In this video tutorial, we will discuss about logarithm and logarithmic function. Let us define logarithm. It is an exponent which b must have to produce y. In symbol, log x base b equals y if and only if b to the y equals x. Here in logarithmic form, the base is b. In exponential form, b is also the base. The value on the logarithmic form y is the exponent in exponential form. So in symbol, in logarithmic form and exponential form, y equals log x base b. And in exponential form, the base b is the same base in logarithmic form. Y is the exponent, which is the value of the logarithm in logarithmic form. Okay. So this is how we change logarithmic form to exponential form. Okay, for example, convert exponential form to logarithmic form. 4 squared equals 16. So this is exponential form. In logarithmic form, this is log of 16 base 4. The exponent is the value of the logarithm. So this is the logarithmic form. Okay. Here in our logarithm, the exponent 2 is the value of the logarithm, which is the exponent in the exponential form, as we define logarithm. Convert logarithmic form to exponential form. So log 1/8 base 2 equals negative 3. 2 here is the base in exponential form. Negative 3 is the exponent in exponential form. Take note of our equivalent logarithmic and exponential form. So our exponential form, 2 raised to negative 3 equals 1/8. Okay, this is our exponential form. Another, what is the value of log 16 base 2? Now we will assign x as the value of log 16 base 2. Then from this logarithmic form, we will change this into exponential form with 2 as the base. X is the exponent equals 16. From this exponential form, we will express 16 as powers of 2. 16 can be expressed as 2 to the 4th power, and both sides of the equation have the same base. We can equate the exponent x equals 4. So the value of log 16 base 2 is equal to 4. Okay, another example. What is the value of log of 1/9 base 3? Let us assign x as the value of this logarithm and change this into exponential form. So 3 to the power x equals 1/9. We will change 1/9 to exponential form with base 3. So 1/9 is 9 to the power of negative 1. And 9 can be expressed as 3 squared. But 3 times negative 1 is negative 2. So 9 to the negative 1 it becomes 3 to the negative 2. Now they have the same base, both sides of the equation. We can equate the exponent x equals negative 2. So the value of log of 1/9 base 3 is equal to negative 2. What is the value of log 1 base 4? So again, let us assign a variable x as the value of log 1 base 4, then change this into exponential form. So 4 to the power of x equals 1. 1 can be equal to any number or any expression raised to the 0 is equal to 1. So we choose 4 as the base because in our left side is 4 as its base. So replace 1 with 4 to the 0. So we have here an equation with the same base on both sides. We can equate the exponent x equals 0. So the value of log 1 base 4 is equal to 0. Another one, what is the value of log 3 to the power of 1 half base 3. So again, let us assign x as its value, then change this into exponential form. Okay, both sides of the equation have the same base, 3. So we can equate the exponent x is equal to 1 half. So the value of log 3 to the power of 1 half base 3 is equal to 1 half. Okay. Now we have types of logarithm. One is common logarithm. Common logarithms is the logarithm with base 10 and is usually written in log or log base 10. So the logarithm of any number wherein you cannot see any base, that means that logarithm has a base 10. Okay. Common logarithms of the powers of 10. So we have here the property log of b to the x base b if the exponential part b to the x has its base b and the logarithmic part as a whole has base b. If they have the same base, then the value of the logarithm is the exponent, which is x. Okay, for example, log of 1000. We can express 1000 as 10 cubed. Oh, you cannot see any base here. It is understood that its base is 10. So, log 1000 becomes log of 10 cubed base 10. So, we have the same base 10. So, in our property, the same base b, the value of the logarithm is the exponent, which is x. So the value of the logarithm is equal to the exponent, which is 3. Okay, another one, log of 100. 100 can be expressed as 10 square, and take note that you cannot see any base here. That is understood as 10. The base is 10. So 100 is 10 square. They are equal 10. So the value is the exponent, which is 2. Another one, log of 10. 10 can be expressed as 10 to the power of 1. So they have the same base, so the value is 1. Log of 0.1. 0.1 can be expressed as 1 over 10 or 10 to the negative 1. So we can change this into 0.1 is 10 to the negative 1. Oh, they have the same base 10, so the value of this logarithm is equal to the exponent negative 1. Another one, log of 0.01. 0.01 is 10 to the negative 2. So the value of this logarithm is equal to negative 2. Okay. Another type of logarithm is natural logarithm. Logarithmic function with base e is the natural logarithmic function. In symbol, log x base e. If the base is e, we change our log into ln, means natural logarithm of x. It is understood that its base is e, a special number, a constant. Okay, for example, log of 1 is equal to 0. This is because ln has its base e. 1 is the same as e to the 0. Any number, any expression raised to the 0 is equal to 1. So they have the same base e. So the value of this is the exponent, which is 0. Okay. Ln of a is equal to 1. This is because we can write this fully as ln of e. E is e to the 1 as its equivalent, and ln has its base e. So they have the same base. The value of this logarithm is equal to the exponent 1. Okay. Another, we have a property of logarithmic function which is called 1 to 1. For any logarithmic function, f of x equals log x base b. If log u base b equals log b v base b, they have the same base, both logarithms of u and b have the same base, then u equals b. So that is our property called one-to-one property. For example, log of 2x base 4 equals log 10 base 4. Both sides of the equation have the same base 4, so we can equate 2x and 10. So 2x equals 10. So solving for x, the value of x is 5. Next, solving logarithmic equations. Now we are ready to solve logarithmic equation using the property that we have learned a while ago. So again, in logarithmic form, log x base b equals y. In exponential form, this is b to the y equals x. So we don't forget the equivalence of logarithmic form and exponential form, because this is what we use in solving logarithmic equation. So example 1. Log of x base 4 equals 2. What is the value of x? So changing this logarithmic form to exponential form, so this is 4 squared equals x. Or interchange left and right of the equation, x equals 4 squared. 4 squared is 16. So the value of x is 16. Another example. Solve for x in log x base 9 equals 1/2. So from logarithmic form to exponential form, 9 the base is the same base in exponential form. 1/2 is the exponent equals x, or x equals 9 to the 1/2. 9 to the 1/2 is square root of 9. Square root of 9 is 3. Okay, so the value of x is 3. Solve for y in this logarithmic equation. Log of y over 3 base 2 equals 4. Change this into exponential form. This is 2 to the 4th power equals y over 3. Then solve for y, or expand first 2 to the 4th. 2 to the 4th is 16. Then cross multiply. 3 times 16 is equal to 48. The value of y is 48. Next, solve for x. Log of 2x plus 1 equals 2. This is understood as the base of this logarithm is 10. So from logarithmic to exponential form, this is 10 squared equals 2x plus 1. Then expand 10 squared is 100. Solve for x. Transfer positive 1 becomes negative. Simplify. 100 minus 1, 99. Then divide both sides of the equation by 2. So x is equal to 99 over 2. Another example. Log of 3x plus 1 base a equals log 10 base e. They have the same base on both sides of the equation. So we can equate 3x plus 1 equals 10. Then transfer positive 1 to the right. So now 10 minus 1 is 9. Divide both sides of the equation by 3. So x is equal to 3. Next, log of quantity 4x minus 3 equals log of quantity 2x plus 5. Both sides of the equation have the same base, which is 10. So we can equate 4x minus 3 equals 2x plus 5. Solving for x, transfer the term 2x to the left and negative 3 to the right. Then simplify. Then divide by 2 so that x is equal to 4. Next, laws of logarithm. The first law of logarithm is about the product. In multiplying, we may take the sum of its logarithms. So multiplication becomes addition. For example, the product of x and y, log of x times y base a, it is equal to log x base a plus log y base e. Okay, so the product becomes the sum of its logarithm with the same base. For example, log of 4 times 5 base 2 is equal to log 4 base 2 plus log 5 base 2. So the product becomes the sum. Second law of logarithm is quotient rule. Division becomes subtraction. For example, log of x over y base a becomes log x base a minus, the divide becomes minus log y base a. For example, log of 45 over 9 base 2 is equal to log 45 base 2 minus log 9 base 2. The third law of logarithm is the power rule. Raising two powers becomes multiplication. Here we have log of x to the power of y base e. The exponent y becomes a multiplier of the logarithm of x base e. So the exponent becomes the multiplier. For example, log of 9 square base 3, 2 which is the exponent, it is equal to 2 times the logarithm of 9 base 3. Okay. Next, solve for x in this logarithmic equation. Log x plus log quantity x minus 3 equals 1. Take note that the logarithmic terms have the same base, 10, and it is the sum of these two logarithms according to the laws of logarithm. We can multiply this. We can combine these two logarithms in a single logarithmic term in which x is multiplied with x minus 3. Okay. So the product becomes addition according to the law of logarithm. Then we can change this logarithmic form after we express the equation in a single logarithmic form. We can change this into exponential form. The base is 10. So, okay. Multiply x and distribute x. X times x is x squared. X times negative 3 is negative 3x. Then change this logarithmic form into exponential form. The base is 10. So 10 to the power of 1 equals this term inside the parenthesis. X squared minus 3x is equal to 10 to the power of 1. 10 to the power of 1 is 10. So simplify. This is a quadratic equation. We will solve this quadratic equation by factoring. Factor of, after we transfer 10 to the left, becomes negative. Then apply factoring. X squared is x times x. Negative 10 is negative times positive. 10 is 5 times 2. So that when we multiply these two binomials, we got the middle term negative 3. After that, equate its factor to 0. So x minus 5 equals 0. Then solve for x. It is equal to 5. Another factor, x plus 2 equal to 0 also. Solve for x. So x is equal to, this is negative 2. Negative 2. We will change it into negative 2 because positive 2 transferred to the right becomes negative. So for your correction. Next example, solve for x. Log of quantity x plus 25 base 3 minus log x minus 1 base 3 equals 3. We can express the logarithm form or term in a single logarithm with the same base. So log of x plus 25 over x minus 1 base 3 equals 3. From logarithmic form to exponential form, so this is 3 cubed base 3 raised to 3 equals x plus 25 over x minus 1. Then expand, 3 cubed is 27. Then cross multiply. Then distribute 27. So 27x minus 27 equals x plus 5. Then transfer the term that involves x. Then solve for x by dividing both sides of the equation by 26. So x is equal to 2. So we will check if x equals 2. Substitute 2 with x in the original equation. Then combine. Then change subtraction to logarithmic form, expressing as a single logarithm. Then change logarithmic form to exponential form. So they are equal. Both sides of the equations are equal. Okay. Next sample, solve for x. 2 log x equals log 2 plus log of 3x minus 4. We will use the law of logarithm. 2 becomes the exponent of x. This addition becomes multiplication, following our laws of logarithm. So this becomes log of x, 2 becomes exponent, addition becomes multiplication, expressing as a single logarithm. Then simplify first. 2 times 3x minus 4. By the 1-to-1 property, we can eliminate the logarithmic form or change logarithmic form to, or we can eliminate log by using this 1-to-1 property. They have the same base, so we can equate x squared equals 2 times 3x minus 4. Then simplify, then solve the equation, transfer this term to the left, becomes negative, this negative, it becomes positive. Then use factoring to solve for x. The factor of x squared is x times x, positive 8 is negative 4 times negative 2, so that when we multiply these two binomials, we have this middle term negative 6. Then equate its factor to 0, x minus 4 is 0, then solve for x equals 4. Another factor, x minus 2 equals 0. Solve for x is equal to 2. So if we check using the value of x, if x is 2, substitute in the original equation. Substitute x with 2. So here x is 2. 3 times 2 because x is 2. Simplify. Expressing as a single logarithm, addition becomes multiplication. Then simplify further, 2 squared equals 4. 3 times 2, 6 minus 4. 6 minus 4 is 2. 2 times 2 is 4. Then they are equal. Okay. 4 equals 4. Using the 1-to-1 property. Another, if we substitute x equal to 4, then substitute, replace x with 4 and this x also with 4. Simplify. Combine, then 4 squared is 16, 12 minus 4 is 8, multiply, log of 16 equals log of 16, so it is equal to 16 equals 16. Next, let us have some values of x which we are going to substitute in our logarithmic function, log x base 1/2. Let us observe what will happen to the value of this logarithm of x base 1/2 as x changes from lowest value up from 1/8 to 8. So from lowest to highest value. Okay, we will use our property log b to the x base b is equal to x. If they have the same base b, the value of this logarithm is the exponent x. So let us substitute x first with 1/8. We can express 1/8 as 1/2 cube because 1 cube is 1, 2 cube is 8. Now, they have the same base. This is 1/2 and the base of the logarithm is 1/2 following this property. So the value of this logarithm is equal to the exponent 3. So the value is 3. Next, if we substitute x with 1/4, we can express 1/4 with base 1/2. So 1/4 is 1/2 square because 1 square is 1, 2 square is 4. So they have the same base. The value of this logarithm is the exponent 2. Okay, so the value is 2. Next, if we substitute x with 1 half, so log of 1 half base 1 half, 1 half is the same as 1 half to the power of 1. So the value of this logarithm is equal to the exponent 1. Okay. Next, if x is 1, we can express 1 as 1 half to the power 0 because any number, any expression raised to the 0 is equal to 1. So they have the same base, 1 half and 1 half with exponent 0 following our property. So the value of this logarithm is equal to the exponent 0. Okay. Next, if we substitute x with 2, so 2 can also be expressed as 2 to the 1 half to the power of negative 1. Because if we change this negative 1 into positive exponent, we will invert the base. We will invert 1 half, that becomes 2. 2 over 1 or 2. So we did not change the value here 2. So they have now the same base. So the value of this logarithm is equal to the exponent negative 1. Okay. Next, if we substitute x with 4, so substitute 4. 4 can be expressed as 1/4 to the power of negative 1. But 1/4 is the same as 1 half square. The exponent 2 multiplied with negative 1, it becomes negative 2. So they have the same base. The value of this logarithm is equal to the exponent negative 2. Okay? Another one, log 8 base 1 half. We replace x with 8. We will express 8 as 2 cubed. Change 2 into 1 half by getting its inverse, and exponent is negative. Okay? So they have the same base. The value of this logarithm is equal to the exponent negative 3. Okay? In other words, as we analyze in our data, with the base b of the logarithm, which is less than 1 but greater than 0, as x increases, so our x here increases from 1/8 to 8, the value of the logarithm decreases. So the logarithm of these values here, this is the values of x, the logarithm of x, as x increases from 1/8 to 8, the value of the logarithm decreases from 3 to negative 3. So this is one observation that we observe in this logarithm of x, where the base b is between 0 and 1. Okay, now let us have another table which we are going to complete. Let us determine the value of the logarithm of x base 2 as x increases from 1/8 to 8 also. So let us substitute x with 1/8. So we can change 1/8 into 1/8 is 1 half cube. Because 1 cube is 1, 2 cube is 8. Then change 1 half into, get the inverse of 1 half, which is 2, and exponent becomes negative. So they have the same base, 2. The value of this logarithm is equal to the exponent negative 3. Next, if we substitute x with 1/4, log of 1/4 base 2, so 1/4 is 1 half square, 1 half becomes 2, but the exponent becomes negative. Then the value of this logarithm will we have here the base 2 and 2 also. It is equal to the exponent negative 2. Okay, if the next value of x is 1/2, change or substitute x with 1/2, and 1/2 is changed into 2 to the power of negative 1. We have the same base 2. So the value of this logarithm is equal to the exponent negative 1. Next, if x is 1, so substitute x with 1. 1 can also be equal to 2 to the 0. 2 to the 0 is equal to 1. So they have the same base, 2. So the value of this logarithm is equal to the exponent 0. Next, if we substitute x with 2, so they have the same base, or 2 is the same as 2 to the power of 1. So the value of this logarithm is equal to the exponent 1. Next, if we substitute x with 4, 4 is expressed as 2 squared, so they have the same base. The value of this logarithm is equal to the exponent 2. Next, if we substitute x with 8, 8 is the same as 2 cubed. Oh, they have the same base, so the value of this logarithm is 3. Okay? Now, our observation indicates that if the base of the logarithm is greater than 1, as x increases, the value of the logarithm increases also. So with b greater than 1, as x increases, the value of the logarithm increases. So this is our generalization as what we observe in our activity completing the table. The direction of the inequality is based on whether the base b is greater than 1 or lesser than 1. So given the logarithmic expression log x base b, we have here log x sub 1 base b greater than log x sub 2 base b. They have the same base, but the base is greater than 0 but less than 1. When we eliminate the logarithm, we will change the direction of the inequality. Greater than becomes less than, or less than becomes greater than. And another observation for the next table, log x sub 1 base b less than log x sub 2 base b. If b is greater than 1, then we can eliminate logarithm without changing the inequality. So x sub 1 less than x sub 2 because the base is greater than 1. Here, x sub 1 less than x sub 2 in our logarithmic form because the base is less than 1 and greater than 0. We change the direction of the inequality. Okay, this is what we will use in solving inequality. Okay, solving in logarithmic inequalities. So, logarithmic inequalities can often be solved just by using the fact that log x base b greater than y. From this logarithmic form into exponential form, we write first x, then greater than the base is the same base in the exponent. Y becomes the exponent. Or log x base a less than y is the same as x equals a to the y. Okay, this is the property that we are going to use in our logarithmic inequalities. If log c base a greater than log d base a, then c equals d by the 1-to-1 property. Take note that we cannot take the logarithm of negative numbers, only positive numbers. Let us solve some logarithmic inequality. Log of 3x minus 1 base 5 less than 1. Take note, we are particular about the base in solving logarithmic inequality. 5 is greater than 1. So we will eliminate or change logarithmic form into exponential form. We retain 3x minus 1 at the left side. These are the property that we are going to use. So 3x minus 1 equals, or rather, less than or equal to 5 raised to the exponent 1. Okay, from logarithmic form to exponential form. Then 5 to the power 1 is equal to 5. Then solve for x. Transfer negative 1 to the right becomes positive. Then combine, divide both sides by 3. So that the value of x is less than or equal to 2. Take note that we have to equate also 3x minus 1 to, rather, this 3x minus 1 must be greater than 0 because we cannot have the value of the logarithm of negative numbers. So 3x minus 1 must be greater than 0 as a condition. So solve for x, transfer negative 1 to the right, then divide its both sides by 3. So x is greater than 1/3. Now, to determine the solution set of this inequality, we are going to plot these two inequalities in the number line. So x less than or equal to 2 on the number line, at the same time x greater than 1/3. So the red arrow pointing to the left, starting from 2 on the number line, because x is less than or equal to 2, so 2 is included. Another inequality, x greater than 1/3. So starting from 1/3 to the right, then the intersection of these two inequalities, the green line, the portion under the green color, is the solution set of this inequality. So the value of x is greater than 1/3 but less than or equal to 2. These are the values which are the solution set of this inequality. So let us check. If x is 1, 1 here is included in the solution set. 1. So if we substitute 1 from the original equation, replace x with 1, then simplify. 3 times 1 minus 1 is 2. Then change this into exponential form. Take note the base is 5. So this is 2, less than or equal to 5. 5 to the power of 1. Simplify. 2 less than or equal to 5, which is true. How about if x is equal to 3? 3 is not included in our solution set. It is outside the solution set. So what will happen if we substitute x with 3? So x is replaced with 3, then simplify. 9 minus 1 equals 8. Then from this logarithmic form to exponential form, 8 is less than or equal to 5 to the power of 1. Simplify. 8 less than or equal to 5, which is false. It is because 3 is not included in our solution set. Okay? If we substitute x with 0, 0 is also not included in our solution set. Then we simplify. 3 times x is 0 is 0. Then the result is log of negative 1 base 5, in which this is against the logarithmic property. We cannot take the logarithm of negative numbers, only positive numbers. Next example, log of 2x minus 1 base 3 greater than log of x plus 2 base 3. Take note that the base is greater than 1, so we retain the inequality and following this property. So we retain the inequality. Log, the base is 3 greater than 1, so we eliminate the log with only the quantities 2x minus 1 greater than x plus 2. So solving for x by transferring the terms to the left side involving x. Solving for x is greater than 3. At the same time, these quantities 2x minus 1 and x plus 2 must be greater than 0. Because we can take the logarithm only of positive numbers. So 2x minus 1 is greater than 0. Solving for x is greater than 1 half. Another x plus 2 greater than 0. X is greater than 2. So we have here three inequalities that we have to plot on the number line. X greater than 3. So we have here x, rather 3. So the arrow pointing to the right. X greater than 1 half. So we have here, where is that 1 half? Okay, this is 1 and 2. Here is 1 half. Between 1 and 2 is 1 half. Greater than 1 half. So directed to the right. X greater than negative 2. Here is our negative 2. From 0, negative 1, negative 2. Greater than negative 2. So directed to the right. The intersection of these three inequalities we have here in green color. This is the solution set of this inequality. So in interval form, the solution set is 3 up to infinity. So open, because 3 is not included in our solution set. This is open. Now let us check. If we substitute a value, for example 4 is included in our solution set. 4 is here. So we will substitute 4 if it checks the inequality, if it satisfies the inequality. So substitute x with 4 here, replace with 4, then simplify. 8 minus 1 is 7. Then the base is 3 greater than 1. We can eliminate log. Then 7 greater than 6, which is true. If x is 2, as we look at here, 2 is not included in our solution set. What will happen if x is replaced with 2? So 2 times 2 plus 2. 4, this is 4 minus 1, 2 plus 2 is 4, 4 minus 1 is 3. Omit log by maintaining the direction of inequality. So 3 greater than 4, which is false. It is because 2, which is not included in the solution set. Here is 2. So that is why the result is false. Next, solve this inequality for x. Log of 2x plus 3 base 1 half greater than log 3x base 1 half. Since the base is 1 half less than 1, between 0 and 1, we will change the inequality symbol. So this greater than becomes less than, omitting the log. The greater than becomes less than. So 2x plus 3 less than 3x. Then solve for x. Simplify. 2x minus 3x negative x less than negative 3. We will divide both sides of the inequality by the coefficient of negative x, which is negative 1. Because we are dividing with negative number, we will change again the direction of the inequality. That is the role of dividing inequality with negative numbers. So x is greater than 3. We will equate also, rather we will add this 2x plus 3 must be greater than 0. And also 3x must be greater than 0. So 2x plus 3 is greater than 0. Solving for x is greater than negative 3 halves. Then we will plot the graph of this inequality on the number line. X greater than 3, so we have here x greater than 3, so to the right. x greater than negative 3 halves. So this is negative 3 halves is negative 1 and 1 half. Here is negative 1 and 1 half. Greater than, so going to the right. The intersection of these two inequalities, the green arrow, is the solution set of this inequality. So from 3 is not included, so this is open, 3 up to infinity. So let us check our solution. If x is 4, 4 here is included in the solution set. What will happen if x is replaced with 4? So replace x with 4. 2 times 4 plus 3 is 11. And omitting the log, because the base is less than 1, change the direction of the inequality. So greater than becomes less than, then simplify. 8 plus 3, 11. 11 less than 12, which is true. It is because 4 is included in our solution set. However, if x is replaced with 2, 2 is not included in our solution set, only the green one. What will happen to the inequality? So x is replaced with 2, simplify. Because the base of the logarithm is 1 half, we change greater than to less than, then simplify further. 7 less than 6, which is false. It's because 2 is not included in our solution set. Okay? Next, let us analyze the graph of logarithmic function. A while ago, we have complete the table. This time we will complete the table of y equals 2 to the x, with the value of x changing from from 1/8 to 6. The corresponding value of y, if x is 1/8, so 2 raised to 1/8, the value is 1.09. If x is 1/4, 2 to the 1/4, the value is 1.19. And x up to 6, 2 to the 6 is equal to 64. Another table, for y equals log x base 2, we will vary our value of x plus from 1/8 to 6. The value of y is taken from log of 1/8 base 2, the value is negative 3. Log of 1/4 base 2, the value is negative 2. Then up to x, which is 6, the value of y is 2.58. Now, this is now the graph of y equals 2 to the power of x, and this one, the graph of y equals log x base 2. Take note that their graph is exactly a reflection when we construct a line, the line y equals x. So we can say that y equals 2 to the x and y equals log x base 2 are inverses. They are inverse of each other. So logarithmic and exponential functions are inverses of each other. Their graphs are reflections of each other about the line y equals x. Next, properties of logarithmic functions. We are going to analyze the graph of these logarithmic functions y equals log x base 2. The domain of this logarithmic function are the set of x's, which are element of real numbers. X is greater than 0. We cannot take the logarithm of 0 and negative numbers. The range is the set of all real numbers. This is the range, all real numbers. It is a one-to-one function. It satisfies the horizontal line test. The x-intercept is 1. Here is the x-intercept. There is no y-intercept. The graph does not intersect the y-axis. The vertical asymptote is the line x equals 0 or the y-axis. there is no horizontal asymptote. Okay? Now, graphing the logarithmic function in the form y equals a log x minus c base b plus d. Now, let us investigate what will happen to the graph of the logarithmic function as we change a, b, c, and d. So, if we vary the value of a in this logarithmic function, supposing we have our original function y equals log x base 2, here is the graph. If we multiply log x base 2 with 2, like this one, the graph becomes the red one, this graph. So what does how does a changes the logarithmic function as we multiply this logarithmic function with 2? So we know that the graph moves up, so it is being stretched 2 units up. So the graph of 2, rather y equals to log x base 2 is stretched up 2 units compared to y log x base 2. So that is how a changes the graph of the logarithmic function. Next, how about b, the base? What will happen to the graph of the logarithmic function? Here, the blue one is our original logarithmic function, log x base 2. If 2, the base, changes down to, from 2, it becomes less than 1. Let us say 1/2. So the base 2 is greater than 1. If it is less than 1, here is the graph of log x base 1/2. Okay? So the graph reverses, starting from up, down. Here in our original function, starting from down, curve up. Okay, that is how the base in the logarithmic function changes the graph, its corresponding graph. Next, what is the function of c in this logarithmic function? Supposing we have here our original function, the blue one, log x base 2, y equals log x base 2. If we add something or subtract x, something from x, so instead of x, we have log x minus 2 base 2. This is its graph. Instead of subtracting 2, we will add 2. Log of x plus 2 base 2. This is its corresponding graph. So what is the change if what changes does c made on the original function y equals log x base 2? If we subtract, the graph is shifted 2 units to the right. If we add, the graph is, if we add plus 2, the graph is shifted to the left 2 units. Okay. Next, what is the function of d in this logarithmic function? Again, our original function is the blue one, y equals log x base 2. If we add something like, or if we subtract, our d is negative 1. If we subtract 1 from the original function, so the graph, or if we add on the other hand, also if we subtract 1, the graph is shifted down. From here, this is the original function, it moves down 1 unit downward. If we add 1 to log x base 2 plus 1, the graph is shifted up 1 unit. So that is the changes of a, b, c, and d in the logarithmic function. So that's enough.